Today we will be focusing on how thermal energy solution facilitates the integration of renewable energy sources in the grid. The proposed plan, we'll see how the discussion evolves, is I'm going to do a short welcome introduction of the project as well as of this knowledge exchange forum concept. Then we will hear about the SINNOGENS project, how you are working with integrating renewable energy sources, followed by a short Q&A, and then the thumbs up approach. We have some preliminary results we want to share with you, and then the most important part, general discussion. On the spotlight, we have Clara Gouveia. She's a member of the board at INESC, representing the SINNOGENS project. And Ricardo. Good morning, Ricardo. Thank you for being here. Then representing the thumbs up, we have Luca Scapino and Manfredi Neri. You are both from Gradyent, and you're developing a digital twin of the systems we're integrating our solutions in. And as keynote listeners, so here to share their experience and ask interesting questions and help me get the discussion started, is Alexander Ledvanov from Heat Consult and Robin Hushmans from the Netherlands Energy Agency. So warm welcome, and let's get to the point. As we all know, the sun does not always shine when we want it to. So those who have, for example, solar PVs on their roof, you don't always get that renewable energy when you need it. And sometimes you have it when you don't use it, right? So what can we do when the production looks like this and the demand looks like that? Well, you can let it be. So you turn off your machines, you turn off your producer, your PVs or the wind turbines and waste it. You can share it. You see a lot more sharing between grids, energy communities, between houses, or you can store it. And this is what we're going to be looking at now. What do we mean by energy storage? Really overall, really simplified, you can store electricity in your batteries. You can store heating, sort of like you can store like in a thermos. You have you keep your coffee warm. Or you can store cooling, same as you have your thermos for your hot coffee, sometimes you have for the cold water when you're working out. We're going to be looking at thermal energy storage. There are a lot of thermal energy storages available out there. They're mainly phase-changing material based, but they're expensive and have environmental issues. They are not very efficient. They work, but they could get improved. They use hazardous materials, and this is one of the important things we're looking at that the European Commission is looking to really change. And their environmental footprint, because of the hazardous materials, because of the production, is huge. And they're hard to integrate. I mean, if you have these buildings, how can you we're looking to develop a plug-in solution that comes in. And this is really where the thumbs up solution comes in. We're developing compact thermal energy storage solutions. That's why our name stands for Thermal Energy Storage Solutions, to optimally manage buildings and unlock their grid balancing and flexibility potential. There was a lot of imagination when coming up with that name, and then the abbreviation thumbs up. Kudos to you. But yeah, I think thumbs up is a lot easier to pronounce and say, a little bit better for the communications part. About the project, we're a consortium of 20 partners, R&D centers, SMEs, and large companies, and we are all over Europe, 9 different European countries, and this is very important to us to get really all the different perspectives. Our goal is balancing the grid one building at a time. Our mission is to gather leading experts in their fields to develop thermal energy storage solutions that are compact, efficient, sustainable, affordable, and scalable. This is quick for those of you who work on European projects. We're almost halfway through the project. It's divided in 3 phases, which I will go into more in detail right now. So right now, we're developing groundbreaking technologies in the labs in Italy, in Spain, and in England. So we have 2 types of concepts. One for based on phase-changing material. It's for the short-term storage, so a couple hours, and one on thermochemical materials, which is a little bit longer term, so meaning a couple weeks, and based on absorption technologies. You can read more about this on our website or contact us, and we will have more knowledge exchange forums to go in detail about these technologies. So this is great. Once you have the prototype is developed and you know exactly how the heat exchanger is going to look, what materials we're going to include, it's going to get tested in a controlled environment. And this is at the Gradyent 3 building in Spain. Once we've tested in this controlled environment, they work, it's not exploding, it's not like leaking anywhere. We're going to take it from the lab to real life. So we're testing in a multifamily building in Spain. It's a retirement home, a single family building, which very modern house, willing to test this technology in their own home. And in a multifamily building here in Gothenburg, Sweden, which is connected to the district heating network. And this lab is literally a lab where people live, and they have like over 22,000 sensors or something like that. It's crazy. Anyway, our goal is to change the future. To do that, once we've proven it works in the lab, it works in real life, we need to replicate, we need to scale up, and hopefully we can have a market rollout by 2030. So that's the project. There are many steps and many things we need to do to get there, and one of them is to engage society and experts. And this is why we have our knowledge exchange forums. We bring together engaged actors to share, inspire, and discuss how to achieve the energy transition. I see many familiar names here. You've participated in very similar exercises that we've done with different focuses. So it's really nice to see you guys coming back. The idea is that we are a sounding board looking at the big picture. So it's a co-creation based peer-to-peer exchange. So really the idea is you ask questions, even if they're difficult, even if they're sensitive, that's the whole point, to get people engaged, get people started. There's going to be a questionnaire at the end. Kindly ask you to fill it out to let us know, okay, what you want us to expand on, and hopefully you'll come back. We support the implementation of sustainable energy smart solutions, particularly our solutions, and we try to look at the whole system. Some of you are familiar with this picture, those who have followed this Celsius for a long time. We want to work with continuous knowledge sharing, this peer-to-peer exchange, looking also through the ThumbsUp project at European policy. How can we understand it? How can we influence it? And how can we act within this? Because it's still very loose, right? Especially around thermal energy storage, what it means, and of course, innovation, replication of scaling. We are not alone, and that's one of the strengths. We are part of a thermal energy storage cluster. We have 4 projects, sister projects. We were all funded under the same call, and we have the same goals. So instead of everybody trying to address the same problem on our own, it's very important for us to communicate not only on the technical, but also on the communications perspective. So if you're interested and you sign up for our contact list, you will not only get the invitations for these knowledge exchange forums. As you've noticed, you get a direct invitation to your Outlook, and the idea is that it makes life simple for you. You participate in the discussions you find interesting, and the ones you don't, you just say no thank you or don't show up, and you're fine. And you will also get our newsletter twice a year and a webinar we organize with our sister projects twice a year. So yeah, that's about us. But now for the really interesting part, I'm really happy and excited to present the SINNOGENS project. You stand for Storage Innovations for Green Energy Systems. So please, Ricardo, if you would like to take over. I don't know if Clara has been able to connect.
Yes, good morning. Sorry.
Good morning, Clara. You're here. Nice to see you.
I just connected on time when you were starting to present the session. Sorry for that. So I will start now sharing my screen. We will divide the presentation between me and Ricardo. So we have been working mainly in one of the let me here just one moment to have here the screens. Okay, so I will start by presenting you a bit the objective of SINNOGENS project and how it's organized, and then we will pass to a more detailed description of Demo 1 in Portugal, where we together with the Faculty of Engineering of University of Porto and also CAPWOT, we are working on the implementation of a multi-energy management system for their industrial park. And that is where the thermal energy storage is a part of this demo. So very quickly, SINNOGENS project involves 27 partners across Europe, distributed along 5 European countries, and we have 6 demo sites with very different objectives and technologies that are being tested. So we have here what we want to show with the project is how we can integrate these technologies, these different technologies of energy storage for the different sectors from industrial, residential, service, agriculture, and mobility. And this is one of the calls that also focus not only on short-term energy storage, but on medium-term storage. So in one hand, we want to develop and showcase a series of energy storage technologies across thermal, electrochemical, mechanical, and also hydrogen. And on top of that, how these different tools can also help manage the energy storage and really respond to the different use cases where these technologies can contribute to the decarbonization, but also to reduce energy costs, of course, complemented with local renewable energy sources. This picture is not very pretty, but it shows the diversity of the technologies that are being considered in the project. So we have from flywheels and ultracapacitors to lithium-ion and flow-based batteries to the thermal heat storage that is being developed in Portuguese demonstrator, to hydro pump, power gas, and geothermal. And on the left, you can see the different objectives where we are integrating energy storage from energy management to reliability services and also to provide support to the grid. So these, as I said, we have 6 demo sites across 5 different European countries, from Portugal, Spain, we have 2 demos, Germany, Switzerland, and Greece. And today we will talk to you about demo 1 in the north of the country in Portugal. So some of the questions for what is the motivation for demo 1? In one hand, we want to demonstrate how energy storage could improve the capacity of managing the microgrids, that in the end, this industrial park is already a microgrid integrating generation, different types of loads from industrial, from service buildings, and also including electrical and thermal loads for the industrial plants that are located in this park, and show how, in terms of energy management, but also in terms of reliability, this storage could help improve the operation. And on top of this, how this adds flexibility to the management of the microgrid to provide services to the distribution and transmission networks. So you have here an overview over the industrial park, where there is already quite significant CHP unit, cogeneration plant, with 7.4 megawatts. I said significant for the load of this industrial park. And this plant provides thermal energy through wood factories that are installed in the industrial park, but it also can provide electricity directly to the medium voltage network. Then it already has a lithium-ion battery with a capacity of 320 kilowatts and almost 800 kilowatt hour that at this point is being operated for basically arbitrage. So it's not considering the load of the plant or the generation. They are also planning to test a vanadium redox flow battery. And as I told you, considering that thermal load is also a significant load for this industrial park, they are planning to test this thermal storage and system. This is a new prototype exploiting a new technology. And so at this point, we are studying different scenarios on how we could integrate these to help support the distribution of thermal energy to these industrial plants. So the main advantage of this industrial park is that Capot is able to test different technologies and different energy management systems, so they can also gain experience and create new solutions to offer to their clients. They are operators of several PV plants and self-consumption installations, and also CHP plants, mainly serving industrial customers. So in this project, what we are proposing and we are working with Capot is to show them the benefits of an integrated management of all these technologies from the electrical system and the thermal system. So what we are proposing them is really to have this system operated as a multi-energy microgrid that is able to minimize the impact of electricity and gas price volatility. And so using their local resources, the PV plants, the electrochemical and the thermal energy storage. And of course, support the decarbonization in this case of the process heat, because in the end, it's one of their most significant loads, and at the same time improve control and monitoring and reliability. This is being developed mainly with Capot, that is the operator of the plant, of course. INESC is responsible for the development of the energy management and power dispatch tool for the multi-energy storage system, and the group from chemical engineering of HILP is developing this thermal energy storage system prototype. So next, Ricardo will present you a bit some of the details of this technology that is being developed by our colleagues, and also how we are integrating this and how we are developing this multi-energy microgrid management tool, and what is new about this tool. So I will pass to Ricardo.
Thank you, Clara. So the first thing I'm going to talk about is the innovative prototype for the thermal energy storage that is being developed. So this is a technology that has many room for improvement, and the new prototype is being focused on these points highlighted here. So responsiveness, charging and discharging times and power, to augment the heat transfer rate, which affects the outlet discharge temperature and the system's energy capacity, and of course fabrication cost, compactness, and other more specific objectives. So please, Clara, can you change? Okay. So in order to do this, the tasks are divided here. The group has started by modeling the prototype through a computational fluid dynamic model. And they also have already been through the phase of surveying alloys for the phase change material, configure the resistors that are important for charging the battery, choosing the heat transfer fluid, and the configuration of the circuit through which the fluid will pass. And they are now in the phase of model validation and optimization. They are also procuring in the market all the necessary components for the assembly of a small-scale prototype, And then, of course, they will simulate their integration in the demo site. So can you change? Thank you. So I believe you're all, or most of you are much more inside this thematic than me, but the main idea with the thermal system here will be to charge the electrical energy, which is going to be passed through those four resistors. So this is the configuration that Philip has come up with for tubes, for rods that will heat the phase change material. In this case, they surveyed two types of alloys, one based in aluminium and the other in tin. And the one that was chosen because of the outlet temperature was the aluminium one. And then to discharge the battery, a heat transfer fluid is passed through that helicoidal tube. So that is also the configuration that they found to be most optimal. And the heat transfer fluid that they tested was air. All these tests were being done through the fluid model, which was made in the ANSYS Flow software. And the idea here is to have two usages for the heat. One is for, as Clara already mentioned, the shipboard factory presses. And the other one is to try to substitute partially or totally a substitute boiler that acts during night shifts for the heating of the complex. So please, Clara, can you change the... Okay, thank you. Okay, so this was for the prototype of the storage system. And now we are also developing an algorithm to optimize the usage of the storage in correlation with the electrical network. So the main idea here, this is a mixed integer nonlinear problem at the moment. And the main idea is to try to minimize the cost of participating in the energy and secondary reserve markets and also the natural gas markets. So the gas network is used to power the CHP. And of course, the thermal storage can charge from the CHP or the electrical network. So everything is connected and everything should be optimized in tandem. This model, this mixed integer problem includes models for the PV systems, the lithium-ion battery, the thermal energy storage, EVs, electrical loads, CHP, and the thermal loads. It's a big model. So can you change, Clara, please? Okay, so this is just an overview of the solution that we came up with. It's a REST API. It has the algorithm inside. We are also focused on the SINNOGENS project to interact with the data space, which we call the SINNOGENS middleware. So we have connectors where we go fetch data such as forecasts for the day ahead generation of the plant. But we also have some information in our service database, such as gas consumption costs, electricity market prices, secondary reserve market prices, and the parameters for the models. And for the moment, this is the solution that we have with CapWatt, is to provide the storage point via a file that we share in an SFTP server. And a SCADA operator can work and see if the schedules are okay, communicate the set points to the BMS. In the future, we are already talking with CapWatt. It would be most advantageous to have an EMS, an energy management system, to which we could communicate directly, and that could overcome the necessity for an operator to actually need to validate the set points. But for now, this is the architecture that we are planning. So please, Clara, can, okay. Now, as I told in the beginning, my disclaimer is that I'm not particularly proficient in thermal energy storage or thermal grids, but our work here in INESC is mostly focused on the electrical grids. We are entering now in the thermal energy storage, but we have much work done in the how to integrate renewables and how to optimally manage electrical storage systems. So we have many recent projects where the main outtakes we took are listed here. I think it's beneficial to say each one of them. So self-consumption optimization and operation cost reduction are actually correlated. And this seems very understandable. And the increased flexibility of a system related to storage capacity and control loads earns greater savings. So arbitrage alone is not always the main motivation, or should be the main motivation for installing storage systems. By including other types of objectives when using the batteries, can have a greater profitability from that type of assets. And this is important for the models that we develop. Good results can be obtained from relatively simple models, which capture the fundamental dynamics of the assets. I'll talk a little bit about this in the next slide. And the potential to provide flexibility service is better achieved through aggregated management of different technologies. So here is the main point to why integrating all the electrical grid and now the thermal grid also is always most beneficial. So we started the SINNOGENS project from a tool that was mainly used for arbitrage of lithium-ion batteries. And here you see the logo of SINNOGENS. These are the new developments to that tool. It is also our intention to, by the end of the project, try to aggregate both tools. So the one that is being developed as a mixed integer nonlinear problem with the thermal energy storage, and this tool. But focusing now on the developments on this tool, we have a better estimation model for the lithium-ion battery, which is being included in the dispatch of the battery, and is based on the rainfall counting algorithm. We also are including a vanadium redox flow model in the mixed integer problem. It's based on those fundamental dynamic characteristics of the battery. In this case, there's a correlation between the discharge energy efficiency and the state of charge of the battery, the discharge power and electrolyte temperature, and the maximum power that the battery can provide, while the voltage is kept constant, is limited by the state of charge. So these dynamics are modeled in a linear model, and they can approximate very well and much better than the usual bucket model, the usage of these type of assets. And we are also considering the integration in day-ahead market and flexibility markets, namely secondary and tertiary reserve. So you can change, okay. Finally, we are also in a parallel line of work coming up with a simulation platform for microgrid islanding and black start, which includes the vanadium redox flow battery and the lithium-ion battery. This model is being done in MATLAB, and they have already performed some simulations where we can see that with the installed capacity, we can successfully isolate the microgrid. And you can see here in the graphics that the event from disconnecting from the grid has that Dirac slope, and then you can see that all frequency, voltage, and active and reactive power are stabilized after, with only the help from the lithium-ion battery and the vanadium redox. So with this, I think I conclude my presentation. Thank you so much for your attention. And I don't know if there are any doubts now, or you can talk later. Thank you.
Thank
Yeah, good morning, everyone. My name is Luca Scapino. I'm a solutions lead at Gradyent. And today with my colleague Manfredi Neri, we'll talk a little bit about, first of all, who we are and what Gradyent does, what is our contribution to the ThumbsUp project. And then Manfredi will also present some preliminary results about our contribution to the project itself. So we are, Gradyent is a European player in the optimization of district energy systems. So our main business is really district heating and cooling networks, also based on steam. We have over 110 experts in energy, data scientists, software engineers, consultants in the energy field. You can see among our background profiles from consultancy like BCG and McKinsey, but also some brands on optimization, energy, and industry-related businesses. We have clients all over Europe and headquarters in the Netherlands, in Rotterdam, and in Germany, in Berlin. And what is our product? So our product is what we call the Gradyent Digital Twin. And I'm fully aware that by now the term digital twin can also sound like a buzzword, and everyone has more or less his or her own definition. So how we intend it is the best virtual representation of the discrete energy system, which estimates in real time the state of the whole system, and acts as a sort of a smart layer on top of the already existing controllers and platforms that district network operators already have in the system itself. We are a software company, so we do not rely on new hardware to be installed, but only on already existing data, if available. A little bit more about operating in real time. This implies also leveraging on available data. So all the sensors coming from the network, it's something we can use to improve our estimation of the state of the system itself. But of course, everything is based on physics and especially on our thermohydraulics models. So there is this kind of a smart overlap between data-driven and physics-based approaches in order to give the most reliable representation of the current state of the network. End-to-end, meaning from the heat production sources throughout the whole distribution network down to the users or the consumers of the heat or the cold in case of a district cooling network. Our solution is in the cloud. It makes use of high computational power, and it has, of course, also a platform that the user can interact with. So after that, the digital twin of the network is built from the heat production sources to the end consumer. It can be used for real-time operational optimization of the network. So it really means setting, for example, optimally the supply temperature of different heat production sources, or even the optimal heat production dispatch from each source, considering also the day ahead or in general the future network demand needs. Considering also all the hydraulic components in the network and the operational limits and costs. And then a second area of usage of the digital twin can also be what we call a design and simulation, which means that after that you have an accurate representation of your system, you can really use it to answer also design questions. For example, what happens in case we add new heat production sources to the network to a certain location? What happens if we add distributed thermal energy storage, or we change the pipelines, or we expand the network towards a new area with new users? So this was more or less at a glance some information about our product, and then more about ThumbsUp. So as Emilia already introduced ThumbsUp as the overarching objective of really decarbonizing the building energy sectors, leveraging on two new technologies based on absorption heat storage or phase change materials. And if you remember from a previous slide, the project is divided into three phases. The development of the technologies, then the validation with the demonstration campaigns on demonstration sites, and the third phase, which is where we are having our major contribution as Gradyent, is the replication campaign. So really selecting some replication sites where the technologies will not be installed, but some analysis and desktop studies will study the potential of integrating the ThumbsUp technologies in those replication sites. So as Gradyent, as I said, we are involved in the replication campaign, meaning that we will simulate the integration of these new technologies, fractless and sortless, for heating and domestic hot water, and we will study the impact on the district heating network and the electricity grid level, also thanks to another partner, Grid Singularity, that will take care of the electricity side of the analysis. And then we study also the impact in terms of reduction of the district heating operating temperatures, if possible, which also means enabling a higher penetration of renewable energy sources that are more efficient at lower temperatures. For example, think about the heat pumps. And then so far, our contribution to the project is that we developed the digital twin of 2 out of 3 demo sites. the one in the Netherlands and the one in Italy. And we are busy in gathering the data for the third replication site, which is the one in Sweden. And on top of that, we are also developing some general thermal energy storage models that are integrated in our digital twin, with the aim of assessing the potential of integrating these two ThumbsUp technologies in the replication sites. So again, this was a little summary of what we are doing in ThumbsUp. I'll leave the floor to my colleague Manfredi for showing some preliminary results on one of the replication sites.
Thank you, Luca. Okay. So thank you, Luca. So my name is Manfredi Neri. I am solutions engineer at Gradyent. Now I would like to present you some of the results. So some of our contributions to this ThumbsUp project, and some of the results we obtained regarding a replication site located in the north of Italy. So this, sorry, can you see the whole screen mode?
Yeah.
Okay, perfect. Okay, so yeah, this replication site is located in the north of Italy. It consists of a district heating network, actually a portion of a larger district heating network. And this portion is characterized by 50 users. It has an overall demand of about 9 gigawatt hour and a peak power demand of about 6 megawatts. So the purpose of our analysis was to study the impact of integrated thermal energy storage solutions in this district heating network. Also to evaluate how thermal energy storage can reduce the morning peak demands. So first of all, we built and validated this digital twin by using historical sensors data. So digital twin consists also of a thermal hydraulic model of the network. So it is able to simulate both the thermal and hydraulic behavior of a network. And so we built it and calibrated by using historical data. On this slide, you can see a proof of the accuracy of this tool, since you can see the comparison between the supply temperature, the historical supply temperature measured in one of the building locations, and also the supply temperature estimated by the digital twin itself. And you can clearly see that the two temperatures are very close to each other when the network is operating. So when there is actually flowing in the pipes, the only time steps where you can see larger differences are when the network is not operating. So when it's off and there is no water flowing in the pipes. And so this proves the accuracy and quality of the thermal hydraulic model. So said that, we continued with our work by considering the installation of multiple thermal energy storages in each of the buildings of this network. Particularly, we consider to allocate a certain thermal energy storage capacity in each building based on the thermal energy required during the morning peaks. So of course, each building has a different demand profile. So then so since the goal of our analysis was to reduce the overall demand of the whole network, we implemented an optimization tool able to optimize simultaneously the operation strategy of each of these thermal energy storages in order to minimize the total peak demand of the whole network, of the whole overall this portion of the network. Yeah. So as a result of this optimization, so the results show that the thermal energy storages should be basically charged during the night, and then discharged, of course, during the morning peaks, in order to reduce the amount of power retrieved by the network during the morning peaks. So basically, to say in other words, the demand peaks in the morning are not supplied anymore entirely by the network, but they are satisfied by the local thermal energy storages. So on this picture, you can see that so the purple bars represent the energy discharged by the storages during the morning peaks, and while the red bars represent the charging during the night hours. You can clearly see that thanks to the optimization, the amount of the energy directly retrieved by the network is decreased by 30% during these morning peaks. So as a result, 30% less power is requested during these peak hours. And this is a significant result, since a reduction of the peak demand can lead to reduce the consumption of other energy sources and the use of backup sources such as gas boilers. And so, of course, this then leads to a reduction of the consumption of gas, and so of the reduction of CO2 emissions. Yeah. Thank you very much.